Today, on AI Paper Slop, we are jumping straight into Qwen-RobotNav by the Qwen team.
Yep, no fluff today.
Right, we're going to deep dive right into it. Yeah. If you're an ML engineer or, building agentic systems, here's a core insight you need right up front. Historically, embodied navigation has been this, it's a heavily fragmented field.
Completely fragmented.
Because different tasks require entirely conflicting visual strategies. So tracking a moving target needs high resolution, recent frames, right? But long horizon object search needs this deep, durable memory that spans dozens of steps.
Exactly.
And the breakthrough with Qwen-RobotNav is that it solves this not by engineering some complex new vision architecture, but by reframing navigation as an observation context modeling problem.
Which is such a smart pivot.
Right. They built a parameterized interface with dynamic token budgets and temporal decay directly on top of a frozen Qwen 3VL backbone. So an external planner can just change the perception strategy on the fly.
It really is a necessary pivot for the field. For years, the community has just been stuck trying to build, a single monolithic model.
The one model to rule them all.
Yeah, exactly. One model that can drive a car at 60 miles an hour and follow complex indoor instructions and track a moving person. But the temporal context requirements for those things are just violently at odds with each other.
It's like trying to use the exact same pair of glasses for reading a tiny textbook and for tracking a fast-moving tennis ball. Just doesn't work.
It's a great analogy because if you're tracking a fast target, say, a drone following a person through a hallway, your model really only cares about the last few fractions of a second.
Right.
Anything older than a few seconds isn't just stale history. It's actively harmful noise. It's polluting your compute.
But then if you're doing object goal navigation like exploring a sprawling office building for a specific coffee mug, your agent needs this massive context window.
Huge. It needs to remember that it already cleared the break room 40 steps ago. Otherwise, it just gets stuck in a loop.
Searching the same desk over and over.
Exactly. And if you look at previous state-of-the-art models, they essentially hard-coded a single assumption about what visual data mattered. So they were basically doomed to fail at whatever task they weren't optimized for.
I like NAVSIM.
Yeah, NAVSIM is a perfect example. It handles memory by uniformly subsampling frames across the entire episode, which, is great for long horizons, but it completely misses split-second changes.
And then the flip side is ABOT-N0.
Right. ABOT-N0 takes the opposite approach. It only keeps a short, fixed, sliding window of recent frames. Great immediate reflexes, but absolute amnesia for what happened 3 rooms ago.
And neither model can adapt mid-flight.
Nope.
So if you've ever tried running a local LLM on your own hardware, you know how fast large context windows chew through VRAM.
Oh, yeah. It's brutal.
So my initial thought reading the premise of this paper was we have massive vision language models now. Why can't we just feed the LLM every single frame from every camera at every time step and just, let its attention mechanism sort out what's important?
In a perfect world, sure. But it comes down to the unavoidable math of computational scaling. It's the token explosion problem.
The dreaded big O notation.
Yeah, exactly. So your total visual token scale is big O of t times, nt being the number of time steps, and n being the number of cameras.
Okay.
If your vision encoder outputs, say, 256 tokens per frame, and your robot dog has 4 cameras, you're generating over 1,000 tokens per step.
Wow, per step.
Right. So if the robot searches a house for 5 minutes at 10 frames a second, T grows linearly. Very quickly, you're dumping hundreds of thousands of visual tokens into the model.
And standard attention mechanisms scale quadratically. Yeah. So trying to process that many visual tokens at high frequency makes real-time robotics just completely impossible.
You'd blow out the memory in seconds.
Right. And even if you didn't, the latency would be so bad the robot would crash into a wall while it was still, thinking about a wall it saw 3 seconds ago.
Precisely. So we can't feed the model everything. And as we saw with the older models, we can't hard-code a single strategy either. That is the genius of Qwen-RobotNav's externally controllable interface.
They decoupled the perception strategy from the model weights.
Yes, they completely separated them.
Let's get into the mechanics of that interface, because I view it sort of like a central bank managing a strict token economy.
Oh, I like that.
Yeah. The external planner acts like the Federal Reserve, just constantly shifting the visual budget between the past and the present, depending on the environment. And they use 3 main parameters to run this economy, right? The total visual token budget, which is B, the temporal decay factor, which is gamma, And the per camera importance weights, which is W sub C.
That economic metaphor holds up really well, especially for the temporal decay factor, gamma. Think of gamma as the inflation rate on old memories.
Okay, inflation rate.
Yeah. If you set gamma to 0, there's no decay. It's uniform weighting. Every single frame from the start of the mission to the current millisecond gets the exact same slice of that token budget B.
But if you crank that decay factor up.
If you crank gamma up to 2, the allocation curve bends really sharply toward the present.
So what does that actually look like for the visual data? Is it just like dropping older frames entirely to save space?
Not dropping them, but drastically degrading their resolution. At gamma equals 2, the math dictates that the most recent frame receives about 7.4 times the token allocation of the oldest frame.
Oh, wow. So 7.4 times the bandwidth.
Exactly. The model dynamically repacks the older images into far fewer visual patches. So it essentially turns the pass into this highly compressed, low-resolution blur while dedicating, maximum 4K bandwidth to the obstacle right in front of it.
That makes total sense. And the system does something similar spatially, right? With the per camera weights.
Right, the W sub C parameter.
Yeah, so if the robot is driving forward, it heavily weights the front-facing camera, maybe a weight of 2.0 because that's where the actionable geometry is. Doorways, pedestrians, hazards.
Things it's about to hit.
Exactly. And then the rear camera might only get a weight of 0.5. It retains just enough tokens for contextual redundancy, like ensuring nothing is sneaking up behind it. But it sacrifices its high-resolution budget to feed the front camera.
And all of this rescaling across time and space happens dynamically. So the sum of all tokens never exceeds that hard budget B.
Right.
But the truly fascinating part is how they trained the model to understand this shifting economy. They use a technique called training time randomization.
Now, this is where I actually have to push back a bit, because the training methodology seems totally counterintuitive.
How so?
Well, during training, every single time the model sees a sample, the parameters are randomized. The budget B, the decay gamma, the camera weights, they're all shuffled. Even the minimum and maximum allowed tokens per image are randomized. Isn't that actively destroying the learning process?
It sounds like it, right?
Yeah, I mean, you are taking the gradient descent process and feeding it warped, distorted, constantly shifting visual inputs. It sounds like chaos.
It sounds like it would induce catastrophic instability, but it actually acts as this massive regularization technique.
Really?
Yeah. If you train a model on a fixed token budget, it overfits to that specific resolution and temporal cadence. By forcing the model to predict the exact same correct physical waypoint trajectory under wildly different visual constraints,
Oh, I see.
you force it to learn the underlying physical geometry rather than just memorizing pixel patterns. Because it survives this randomized chaos during training, it generalizes flawlessly at inference.
That is incredibly clever. So you can hand the planner any configuration of dials, and the frozen backbone just intuitively understands how to interpret the observation.
Exactly.
Which brings us to the architecture itself. We have this incredibly complex shifting visual stream. And my immediate assumption reading this was, okay, they must have built some custom cross-attention modules or like a heavy temporal encoder to inject this into the LLM.
Nope. They didn't touch the architecture of the Qwen-3 VL backbone at all.
It's entirely unmodified.
0 architectural modifications. They didn't even add specialized spatial temporal blocks. The only addition is the action head, which is remarkably simple.
This was the real aha moment of the paper for me. The action head is just a lightweight 4-layer MLP, a multi-layer perceptron.
Literally just 4 layers.
For anyone listening, an MLP is basically the most standard vanilla neural network layer you can possibly build. And this tiny 4-layer MLP takes the final hidden state of the language model, which usually outputs text tokens like the word apple, and it just maps it directly to 8 continuous physical waypoints.
The XY coordinates and the heading.
Yeah, it's crazy.
It just highlights how rich the latent representation of a modern vision language model really is. The Qwen-3 VL backbone already understands deep spatial geometry, depth, and semantics just from its pre-training.
Right, it already knows how the world works.
Exactly. So the MLP is just acting as a simple translator. It projects that complex latent understanding into a continuous 2D physical plane.
And because they didn't modify the backbone, the way they feed the temporal and spatial data into the model is purely through natural language, which is so elegant. They use what they call the embodied prompt.
Oh, the prompting strategy is great.
It's like treating the robot's cameras as participants in a group chat, just posting time-stamped images directly into the text stream.
Yes. The input prompt literally reads like a log file. It says, plus timestamp1 camera, front, followed by the compressed image tokens for that view, then plus timestamp1 camera.
Right.
And those tokens.
Just a text log.
Because Qwen3VL natively understands sequential text, it implicitly learns the temporal order and spatial layout just by reading those tags. No custom positional encodings needed at all.
And I found the embodiment preamble equally clever. Before the images even start, the system prompts the model with a role-play identity. Like, you are a robot or you are a car. It feels like a standard system prompt, but it has massive downstream effects.
Because it acts as a powerful task prior. I mean, think about the internet-scale data these models are trained on. By defining the embodiment as a car, you instantly activate the model's latent knowledge regarding traffic rules, lane markings, and, high-speed multi-agent dynamics.
And if you say you're a robot,
it shifts its attention priors toward indoor layouts, avoiding furniture, navigating tight doorways. It's just a zero-cost way to recruit the correct subset of its massive world knowledge.
So we have the backbone, the shifting token economy, and the MLP translator. But who is actually driving? Because Qwen-RobotNav is highly configurable, but it clearly needs an orchestrator.
Right, it needs a boss.
Exactly. This brings us to the two-tier agentic system, which is critical for long-horizon tasks, like embodied question answering. Let's say you ask a robot, is my green coffee mug on the kitchen counter?
Which is a seemingly simple question that requires massive reasoning. The robot doesn't know where the kitchen is, let alone the mug.
Right.
This is where the upper tier planner, which in their framework is Qwen 3.6 plus, takes over. The planner acts as the prefrontal cortex. It breaks the broad goal into sequential sub-goals and dispatches them to Qwen-RobotNav, which acts as the cerebellum, the reactive executor.
And the planner is the one actually turning the dials on our token economy mid-episode. So when the robot first spawns in a hallway, the planner's sub-goal is, explore and find the kitchen. So it tells Qwen-RobotNav to set the token budget B high and the decay factor gamma low.
Right, it creates a broad, uniform memory so the robot can map the environment.
But the moment the cameras spot the kitchen counter, the planner issues a new sub-goal. Approach the counter and scan for the green mug. And it dynamically twists the dials. It lowers the total budget to save compute, but cranks the decay gamma way up.
So suddenly, Qwen-RobotNav drops its memory of the hallway and hyper-focuses all its visual resolution on the immediate frames.
To precisely track the counter and avoid bumping into the kitchen island. So it's really treating Qwen-RobotNav as a highly configurable, intelligent steering wheel waiting for the planner's orders.
But wait, what happens to the memory of the hallway? If Qwen-RobotNav is decaying its visual history to focus on the counter, doesn't it just forget the house layout?
It would, which is why the system maintains a two-level memory. So Qwen-RobotNav handles the short-term, immediate trajectory rollouts. But the upper-tier planner maintains a persistent cross-episode evidence notebook. The evidence notebook. The text compression here is so brilliant. Instead of trying to save thousands of high-res frames of a kitchen to prove it searched there, the evidence notebook just stores a highly compressed text entry.
Yep.
It literally just logs a string, like step 47, kitchen entered, countertop checked, no green mug observed.
By compressing dense visual history into durable semantic text, the planner avoids the token explosion entirely.
It preserves conclusions.
Right, like searched regions or rejected hypotheses. So the agent stays focused over episodes that might take hundreds or thousands of steps without dragging this massive anchor of raw pixel data behind it.
But to build an executor capable of translating all this into physical movement, it requires a monstrous amount of training data. And the data soup they cooked up is 15.6 million samples, split 85% to 15%.
It's a very specific split.
Yeah, I want to start with that 15% because it's purely vision language data. We're talking VQAV2, CLVR, general visual grounding datasets. Why are they feeding a navigation model static visual question answering data?
Well, it's to prevent what's known as reactive collapse. It's a pretty well-documented phenomenon in robotics.
Okay.
If you fine-tune a massive vision language model purely on trajectory data, like just mapping pixels to steering commands, it suffers from catastrophic forgetting. It basically devolves into a simple reactive action sequence mapper.
So it essentially forgets what a refrigerator is and just learns it's a block of pixels to steer around.
Exactly. And you need the model to know what a refrigerator is to answer the prompt, go to the kitchen. So by co-training with that 15% VQA data, They anchor the model's semantic understanding. It preserves the deep perceptual substrate you need to read a street sign or infer the layout of a complex room.
That makes perfect sense. But the other 85% of the data, the navigation trajectories, is where the real black magic happens. They built an automated text-to-video, or a T2V pipeline, to synthesize this data. Let's break down this four-step process because it solves a massive bottleneck in embodied AI.
It really does.
So first, an LLM generates a prompt and a navigation instruction. Second, a text-to-video model renders a first-person egocentric video based on that prompt. But here's where I get hung up.
The 2D problem.
Yes, if the text-to-video model is just hallucinating a flat 2D video of a shopping mall, how does the system extract actual 3D physical coordinates to train the robot's steering? I mean, it's just pixels on a screen.
That is the third and fourth step of the pipeline. They pass that synthesized video through a monocular depth and pose estimator.
Okay, what does that do?
It's a specialized model that looks at how pixels shift from frame to frame in a 2D video and mathematically infers the camera's ego motion, its movement through space. Plus, it generates depth maps for the environment, so it literally reverse engineers a mathematically rigorous 3D navigation path from the generative 2D hallucination.
That's wild. And they also use a vision language model to filter the videos first, right? Because generative video is notorious for objects melting or, physics breaking.
Oh, absolutely. The VLM acts as a quality control bouncer. It throws out any videos where the physics violate reality. That ensures the depth estimator only extracts trajectories from physically plausible spaces.
But I have to ask, why go to all this immense effort to generate synthetic video? Why not just spin up millions of parallel agents in a traditional 3D simulator like Habitat?
Well, simulators like Habitat are fantastic, but they suffer from a severe visual domain gap.
Meaning they don't look real enough.
Right. 3D assets are finite. You end up with agents that have perfectly navigated the exact same rendered couch and identical oak texture 10,000 times.
Over and over.
Yeah, and then when you put them in a real messy apartment with weird lighting and shadows, they just fail. The text-to-video pipeline allows them to synthesize infinite photorealistic diversity. Crowded markets, rain-slick streets, brutalist architecture, all without needing an army of 3D artists.
So we have the dynamic token economy, the MLP action head, the agentic memory, and 15 million samples of synthetic video data. Does it actually work when you drop it onto physical hardware?
The benchmark results are incredibly strong. They tested it across multiple highly standardized tasks. On VLN-CE RXR, which tests complex instruction following in unseen environments, it had a 76.5% success rate, which is state-of-the-art.
Wow.
And on EVT-Bench, which measures active visual tracking of moving targets, it maintained a 90.0% tracking rate. They even tested it on NAVSIM, an autonomous driving benchmark, where it achieved a 91.4 PDMS score. That measures driving precision and safety.
And it scales beautifully, too. The 8 billion parameter version of the model noticeably outperformed the 2 billion parameter version, which basically proved that adding more raw capacity allows the model to build a stronger, shared spatial planning substrate.
Yep, scaling laws hold up.
But I really want to focus on the real-world deployment, because they took this 8 billion parameter model and put it on a physical Unitree Go-To robot dog, powered by an onboard NVIDIA Jetson Thor compute module. They ran an experiment comparing cloud inference versus edge deployment, and the results are just a masterclass in systems engineering.
It really highlights the hidden dangers of robotics. When they offloaded the model processing to a powerful remote cloud server, the average latency was very fast, 196 milliseconds. But because of network fluctuations, they experienced massive latency spikes, jumping all the way up to 800 milliseconds.
And if a robot dog is navigating a flight of stairs, or an autonomous car is reacting to a pedestrian, an 800 millisecond network stutter isn't just an annoyance, it's a catastrophic physical failure.
Which is exactly why the edge deployment is so critical. By running the model directly on the robot's Jetson Thor hardware, they eliminated the network entirely. To make an 8 billion parameter model run locally, they used FP8 quantization.
That compressed the model's complex mathematical weights into smaller 8-bit chunks to save memory, right?
Exactly. And they ran it through TensorRoute, which is NVIDIA's hardware acceleration library.
And the result was an average latency of 204 milliseconds. Slightly slower than the cloud's average, but incredibly stable. No spikes.
Zero spikes.
This is a massive lesson for anyone deploying physical ML systems. A stable 204 milliseconds on the edge is infinitely more valuable for a moving robot than a faster server-side model that occasionally stutters for nearly a second. Control algorithms can easily plan around a consistent 200 millisecond delay. You cannot plan around a random 800 millisecond network drop.
Exactly. The fact that they can run this multi-camera, high-frequency visual stream locally on a robot dog is a direct testament to the efficiency of that token budgeting system and, the lightweight design of the MLP action head. They stripped away all the heavy architectural baggage.
It really is a masterclass in constraint. So to wrap up the philosophical shift of this paper, Qwen-RobotNav proves we don't need siloed, highly specialized architectures for every individual robotic task. We don't need to train a dedicated tracking model and a separate exploration model. We just need a unified foundation model equipped with a configurable lens for how it views its own history and environment.
Yes. And by handing an upper-level planner the controls to that lens-shifting token budgets and temporal decay on the fly, incredibly complex, adaptable behavior just naturally emerges from a simple foundation.
It fundamentally changes how you look at processing context. And I actually want to leave you, the listener, with a provocative thought that builds on this idea. We've spent the last 20 minutes exploring how machines use task-adaptive token budgets to survive an overwhelming flood of visual data. But what if we applied that exact mathematical framework to human cognition?
Oh, that's interesting.
Right, because if you are navigating your own daily token explosion, Slack messages pinging, emails stacking up, a dozen research papers open in your browser, are you stuck in a rigid, fixed context mode? What if we could actively train ourselves to adjust our own decay factors and attention weights based on the task at hand? What would it look like to consciously zoom in on the immediate high-resolution present when we need to execute, and deliberately widen our context window when we need to explore, just like Qwen-RobotNav does? It's something to mull over the next time you find your own context window blowing out.